This series of lectures is going to talk about organic chemistry. So, what do we mean by organic chemistry? So, organic chemistry is the study of compounds where carbon is the main element. So, this compound doesn't need to be made by living organisms, which is a common misconception. It just has to contain carbon as the central element in it. So very often these these compounds are made by living organisms or used by living organisms, but that's not a requirement. So that's all we're talking about with organic chemistry. We're going to see in this series of videos that plastics, for example, which are completely man-made, are organic, containing lots of carbon, but they are definitely not made from living organisms insofar as, we make them, but they're not made by an organism as far as them excreting it or something like that. If it's not an organic chemical, then it is a inorganic compound. And so the study of all other compounds that are not carbon-based is inorganic chemistry. The thing is that organic chemistry is actually the biggest section of chemistry because most of our known compounds are organic. So here's just a short list of organic compounds. So gasoline, plastics, alcohols, foods. So pretty much, all of the foods that you eat are going to be organic as far as the containing carbon. Flavorings, pretty much anything that you run into on a daily basis is an organic compound unless it's made out of something like pure metal. So lots of organic compounds around us every day. So why carbon? Why carbon as the main molecule and not something else? So the first thing is, what is the valence of carbon? So if you've watched the earlier videos, then you'll know that we've talked about valences, and valence electrons are those electrons in the outermost shell that are available for bonding. And the valence for carbon is 4, meaning that it's got 4 electrons in that outermost shell. So what does that mean as far as the number of bonds it can make? Well, the octet rule, or what we talked about, is that outermost shell needs to have 8 electrons. So that's why we call it the octet rule. I can't remember if I talked about that in previous videos. So the octet rule states that to be a happy stable atom, you need 8 electrons in that outer shell. And so a single carbon atom can bond to up to 4 other atoms. That's what makes carbon so useful for creating compounds, because each single carbon can bond with up to 4. And so if you get something like what you've got over here, we've got 1 carbon bound to 4 hydrogen, but here we've got them bound in a chain, and there's only 1 bond between each of these carbons, which means that this carbon right here is only using 2 of its 4 bonds, so it can bond to 2 more atoms on either side. This one out here can actually bond to 3 more because it's only used 1 of its bonds. So it allows for a large amount of variability. In fact, the combinations to make organic molecules are almost unlimited because every time you add another carbon, you add more variability. But they do fall into patterns that we can group. And so we can make them into groups, for example, that are unbranched. So what you see here, we've got branched ones, we have ones that form rings. So they do fall into pattern groups. Now, the big group that we will be looking at a lot are the hydrocarbons. So hydrocarbon for hydrogen and carbon being the only atoms that you find in the molecule. So it is an organic compound that just contains hydrogen and carbon. The simplest hydrocarbon is methane. So CH4, this is the structural formula for it. So carbon surrounded by 4 hydrogens. This is actually the model that was on the slide before. Let me back up. So this is methane right here. This is what it actually looks like. This is its structure in 3D. So, so that's the simplest version we can get of a hydrocarbon. But from there are thousands of possible arrangements, because you can just keep adding a carbon. So here we have ethane that has 2 carbons on it. Then you can add one more, and then one more, and one more. And we can just keep adding carbons. So we can make those chains longer and longer and longer. And like I said, they can be chained, they can be branched, they can form into rings. So lots of different arrangements available. The other thing that can happen is what you can see in this diagram down here. And that is that the carbons can actually have single bonds between each other, like you see here in ethane. They can have double bonds in ethane. Yeah, I know, the names are great. But this ENE indicates that there's a double bond between the carbons. And then ethine has a triple bond between it. And so each time you go up in the number of bonds between the carbons, you reduce the number of hydrogens that are there, which again changes the format. And so that octet rule, oops, sorry, I was trying to grab my head, there we go, is still in effect, so that it still needs to make 8 bonds. So the number of hydrogens changes, right? So here you've got 6 hydrogens. Double bond between the carbons means that there's only space for 4 hydrogens on the molecule. And now we've got a triple bond between the carbons, so there's only space for 2 hydrogens on the molecule. So, like I mentioned, there's lots and lots of options for their structure. They can go branched, they can go straight line. Here is an idea to give you an idea of what they can do. So these are all pentane. So 5 carbons for penta. And these are what we call structural isomers, meaning that they have the same molecular formula, but different configurations. So here, this is N-pentane, then we have iso and neopentane. You don't need to know the different names. That's just how we name them, so we can indicate which form they're in. And so we've got the drawings down here of what they look like, and then the 3D models. So you can see what they would look like in 3D space. So N-pentane is the straight chain version. You might go, well, that doesn't look straight. The bonds make the bends in the molecule. But if you look up here, it is a straight chain molecule when you get all of the atoms laid out. So this N-pentane is going to be straight. Isopentane, the carbons are arranged differently. So the carbons are now in a branched pattern instead of a straight chain. So we have a semi-straight chain here, but we have a branch coming off the top. And so this reorganization gets you this rough shape you see down here. And that's definitely the shape we see up here, right? So we've got the kind of straight line down here, but then we have that branch coming off the top. And then neopentane forms an X. Now you can see when you do the 3D model, it's not a true X as what we would expect. The 4 branches go into different directions to make a 3D model version of that X, but you can see you get very different configurations, and these change the properties of the molecules. So for example, with these 3 versions of pentane, it changes the boiling point. So the boiling point of pentane is 36 degrees Celsius. Isopentane is 30 degrees Celsius, and neopentane is 10 degrees Celsius. So some of these will boil at room temperature. Basically, they'll turn into gas at room temperature. pentane only boils when it gets close to our body temperature. So that makes a big difference based on what you might want to be doing with these, on which version, which structural isomer you have. Now, carbon always forms 4 bonds, always. It's going to do it in one way or another. And so we've got the diagram, the dot diagram that we saw in a previous video, but now we're only generally going to see it drawn this way. This is the shorthand for a covalent bond, where they're going to be sharing those electrons. So rather than having to draw all the dots out, we're just going to shorthand and draw it as a single straight line. All right. So here are some other diagrams. These are butane and butene. The difference is, again, that double bond between one of the carbons. Well, I'm sorry, 2 of the carbons. And what I want to talk about with these two, and we could talk about the same thing with ethane and ethane, is saturated versus unsaturated hydrocarbons. So what we've got here, butane is what we call a saturated hydrocarbon, and butene is what we consider an unsaturated hydrocarbon. So what does that mean? Well, the difference is because of this double bond. So whenever there's a double bond, that creates a unsaturated hydrocarbon. Unsaturated organic molecules don't contain the maximum number of hydrogens that they could contain. So because there's this double bond between the carbons, that loses hydrogens. So you can see here, butane should have 10 hydrogens, but butene, because of that double bond, has only 8 hydrogens. Right? It could have 10 if it gave up that double bond. And so the unsaturated organic molecules that you come across, whether they're hydrocarbons or other versions, we'll see a couple of other types that aren't just hydrocarbons but have other atoms like oxygen and nitrogen in them. But they are going to become unsaturated because of these double and triple bonds. So why do we care? Well, when they have these double and triple bonds, they are actually less stable and therefore more reactive. And that's something we need to know. When they are more reactive, they are more likely to react with other chemicals. They are more likely to, in the case of hydrocarbons, be explosive. So these are things that are good to know whether they're unsaturated or saturated. So how reactive could they be? Well, you actually likely know an unsaturated hydrocarbon. So this is our friend from before. Now we saw it with a different name on an earlier slide in this video. This is ethylene. Sorry, I even get them still confused. But this is acetylene. So this is ethane where it's lost its hydrogens and has a triple carbon bond. And so the common name for it is acetylene because its actual name is kind of mouthful to say. And so acetylene is incredibly reactive because once you ignite it, along with oxygen, it can burn up to 3,000 degrees Celsius, which is insanely hot. Some of you may be familiar with acetylene gas. This is the gas that is used, as you can see in the picture, by welders because that temperature is hot enough to melt almost any metal. And so it's incredibly useful for that. But the reason why is because it's so reactive due to that unsaturated bond set. All right, the last thing that I want to cover in this video is aromatic hydrocarbons or aromatic compounds. So these are still generally hydrocarbons. You can see this guy down here. He's not a hydrocarbon. He's got some chlorine on him. But these guys are aromatic, meaning that they're going to have an odor. But they have this benzene ring structure. So they are going to be drawn as these hexagons with a circle in the center. And what that is showing you is this. So you've got 6 carbons and 6 hydrogens that are creating this ring bond set. Why are we drawing a circle? It's because there are 3 double bonds in here. So that's why there's only 6 hydrogens. But the double bonds, if you look at this picture, the double bonds move. And so those double bonds rotate around inside of these carbons, and they're never in the same place. And so that's why we draw them as a circle. Okay, so those bonds, I know it sounds weird, but those bonds actually do move. And like I mentioned, these guys have odors, unlike other hydrocarbons. So something like propane or methane actually does not have an odor to it. We have to add an aromatic compound, like one of these aromatic hydrocarbons, in order to be able to smell it. Some of these you may be familiar with. Toluene. Toluene is often a paint remover, a stripper of different types of materials. Like I know it's in some paint strippers, it's in some nail polish removers, very odoriferous. Naphthalene. Naphthalene you may know if you've ever used mothballs. It's the smell of mothballs. It actually is why mothballs get smaller, because it converts into the gas form, and that's why you can smell it. And dichlorobenzene, this one you've likely smelled as well, because this one is used in commercial room deodorizers, so like bathroom deodorizers and so forth. All right.